All right, welcome everyone. Good morning. We are Astro Group 2, and our project is on identifying stars associated with our Lyrae in the Milky Way halo. My name is Brad Chen, and I go to Langley High School in Virginia, and I'm a rising junior.
My name is Rehan Dias. I go to Oberoi International School in Mumbai, and I'm a rising senior.
My name is Kaho Ishihara, and I go to Bergen County Academies in New Jersey, and I'm a rising junior.
We've been working on this project under the mentorship of Abby Badley and Dalia Gregoria Chas, and our research collaborators are Dr. Yuting Feng, Professor Raja Guhurta, and Dr. Eric Peng. So quickly going over some basic terminology that we're going to be using throughout the course of this presentation. I'll start by explaining what the Milky Way halo is. So it's the spherical component of the Milky Way in which the disk is embedded, as you can see in the image over there. It's made up of old, low metallicity stars, globular clusters, and dark matter. It has relatively low stellar density, which means that for large areas in space, there are a really few number of stars. The radius of this Milky Way halo is around 1 million light years, which shows us how big the Milky Way truly is. So coming back to the fact that I said there's low metallicity stars in the halo, metallicity is the fraction of elements heavier than helium in a stellar object. So a higher fraction means a higher metallicity and a lower fraction is a lower metallicity. Now going over stellar evolution, so the graph we can see on the right is a HR diagram, which is a plot of luminosity on the y-axis versus temperature on the x-axis. It has three main parts, which is the main sequence, the red giant branch, and the horizontal branch. The stars that we're focusing on specifically are called RR Lyrae, and they're a subset of the horizontal branch, which is seen by the light blue filled circles on the diagram there. So the shape of this graph mimics something that we've created in our research called an isochrone, which is the locus of stars with the same age but different masses. And we'll go more into this later.
All right, so in our research, we're using this special type of star called an R Lyrae. So what R Lyrae are that they're stars that expand and contract, and their brightness varies accordingly. They have a period of around 6 to 18 hours, and the really useful thing about them is that they have a very strong period to luminosity relationship. So what that means is that based on their period and their apparent magnitude or their apparent brightness, we can very easily find their absolute magnitude, or in other words, their intrinsic brightness. And once we have their actual absolute magnitude, we can very easily find the distance to these R Lyrae, as further stars will be dimmer and closer stars will be brighter. And another really important things about these R Lyrae is that they're very easy to identify. As you can see in this image below, it pulses every this video is obviously sped up, but this in reality this would pulse every 6 to 18 hours, and this makes R Lyrae really easy to identify. So data sets of R Lyrae will often be very uncontaminated, which is very good for our research. I would also like to mention that we are using 180 new R Lyrae discovered by Yuting, Raja, and Eric. So we'd like to acknowledge them. So now, what is the goal of our project? Our goal is to identify stars associated with R Lyrae in the Milky Way. Now, how are we going to do this? Well, since we know the distance to all these R Lyrae, we're going to use them as distance markers to kind of find the geometry of the Milky Way and find associated stars. And we can do this because we can use the R Lyrae as an anchor to anchor the isochrone, and all of the non-R Lyrae that are more common will fall along the isochrone. And that's because stars that are born at around the same time and are located in the same region will often have similar properties, which is represented by the stars that fall along the isochrone. So why exactly are we doing this? Well, we're doing this because if we find associated stars to these new R Lyrae, then we can better understand the geometry and extent of the Milky Way halo. And this will allow us, this is like a stepping stone for other research to build upon us, studying things like dark matter, galaxy formation, or galactic cannibalism. Now let's take a look at our data. So this is the next generation Virgo cluster survey, otherwise called the NGBS survey. It was taken by a telescope in Hawaii. So on the left-hand side, you can see what the NGVS survey looks like in the visual wavelength spectrum. And on the right-hand side, you can see what the footprint of the NGVS survey looks like. So as you can see, it's actually a very small portion of our sky. Now let's take a closer look at our data. So this is the filtered point source catalog of all the NGVS stars. And then this is all 180 R Lyrae, and this is where they fall on the survey. And this is a 2D histogram of the NGVS survey, all the stars in the NGVS survey. And what this means is that this graph shows you the relative density of all the points on this graph. So you can see these really bright spots there. That means there's really a lot of stars, and it's like really dense over there. And we'll talk about what that means in the future, but just keep this in mind for now.
Okay, so let's go over the magnitude system. So for measuring the brightness of astronomical objects, we use something called a magnitude scale. It follows an inverse logarithmic scale, which means that a lower brightness means it's brighter, and this extends into the negative region as well. Think of it as a geometric progression rather than a linear progression, as each step changes by a difference of 2.5 times. So a difference of 1 magnitude would be 2.5 times dimmer, for example, and a difference of 5 would be 100 times dimmer. Next, quickly going over color. Color is the difference between two magnitudes measured through two different filters, and it's the ratio of energy emitted at these two different filters. In our research specifically, we'll be focusing on the G or green filter and I, which is the far red or infrared filter. These filters correspond to the wavelengths of 480 nanometers and 750 nanometers respectively. Color in astronomy is used to measure temperature, where bluer is hotter and redder is cooler. So in our research, something that was really important were color magnitude diagrams, where color is the difference between the magnitude in two different filters, and magnitude is the brightness in one filter. So as we can see on the x-axis, we have our color, which is G minus I, or green minus infrared, and our y-axis is the I band or infrared magnitude. So as we can see, this shape is an isochrone. As I mentioned earlier during stellar evolution, it follows a similar shape because all of these stars are around the same age, but just have different masses. So we use this to find associated stars with Aurora Lyrae. And one quick thing I'd like to add is the concentration shaped like a hockey stick towards the bottom of this isochrone is the Sagittarius stream.
Now I will be explaining what the Sagittarius stream is. The Sagittarius stream is a stellar stream created from the remnants of the Sagittarius dwarf galaxy. This dwarf galaxy was ripped apart by the gravitational pull from the Milky Way halo, leaving a trail of stars, as you can see in orange here. And because of this, a lot of the stars from the Sagittarius stream are contained in the foreground of the region of the sky we are studying. So moving on our CMDs, we plotted isochrones to predict where associated stars would lie on the CMD. We did this by shifting the isochrone based on the distance from the Aurora Lyrae to the Earth. What this means is if the distance to the Aurora Lyrae was relatively close, we would shift the isochrone to a brighter position. And if the Aurora Lyrae was at a relatively further distance, we would shift it to a dimmer position. By repeating this 180 times, we were able to find a concentration at 35 kiloparsec. Kiloparsec is a unit of distance, and it's about 3,260 light years. As you can see on the CMD, this corresponds to where the Sagittarius stream lies. This means that stars in the Sagittarius stream are associated with the Aurora Lyrae at 35 kiloparsec. This is another CMD, and you can see the Sagittarius stream. Because the Sagittarius stream is relatively close to us, we decided to cut this out so that we can see the background stars better. And so now our CMD looks like this.
Now let's talk about reducing the background contaminants. So as you can see, this is a side-by-side view of the NGVS survey, and the bright spots on the visible wavelength spectrum correspond to the red circles you see on the right side. And those are the very dense regions I was talking about earlier. So what those are globular clusters. And globular, to give you some context, globular clusters are a very dense set of stars, containing upwards of 1 million stars. And what happens is that these globular clusters are so densely packed with stars that when the telescope is looking at them, it cannot like individually resolve every single source of light. So it often combines multiple sources of light, which amplifies every single source of light, which makes it a lot brighter and look a lot closer to us. And this skews our results. So we want to remove them. This is what our data looks like after we remove these clusters. And now let's see what happens on a CMD. So this is the original CMD with the globular clusters. All these red points highlighted are the points that we're trying to cut out, which are the globular clusters. Then this is the new CMD with the globular clusters cut out. So take a look inside the red circle and you can see that we are clearly removing a big concentration of stars here.
To find more associated stars, we decided to take a smaller region around each RLI. In the red circle here, we wanted to see if the stars have associated stars. We specifically took a 1-degree region around each RLI and repeated this for all 180, which now looks like this. Using this, we created more CMDs. This CMD specifically plots the first isochrone shifted to the distance of the first RLI and the stars that are in the 1-degree radius for the first RLI. As you can see, the stars clearly follow the isochrone shape, meaning that those stars are likely associated with the RLI. We can repeat this process for all 180 RLI to find their respective associated stars. Our isochrone data originally did not have a horizontal branch. However, later in the research, we wanted to use a horizontal branch to find additional associated stars. So we decided to use a CMD of a globular cluster with similar metallicity as our isochrone as a template. As you can see in blue, we manually added points along this template to create our horizontal branch. After this step, we placed everything on a CMD and were able to find additional stars, which are represented at the top.
Okay, so next we wanted to verify our results through something called the association test. So what this is that we had a set of real data, which was each RLI rate and its corresponding distance. But then we also wanted to create a fake set of data. So we did this by using the same RLI rate, but shuffling the distances of each RLI rate. And this would help us because if we could still see similar trends, we would know that it's just coincidence and there was no actual correlation between the distance and the associated stars. So as you can see on the top, that's the first RLI rate, which has a distance of around 26.8 kiloparsecs from us. But the bottom one is RLI rate number 179, which has a distance of 296.3 kiloparsecs. So we can see a clear difference in the distance from each point on the graph to the red line, which is our isochrone. So for real data, we expect that each point minimum distance to the red line would be closer to 0 as it follows a similar trend. But then when we shuffle this distance, you can see that each point will be much further away than it should be. So we wanted to use this to verify our results. And to do that, we plotted it on something called a histogram. So as we can see here, for our true data, we had a really large concentration around 0, whereas our fake data did not follow the same pattern, showing us that we truly had some promising results.
Our research is not yet complete, and our mentors, along with our other research collaborators, will continue working on this project to find associated stars for distant RLI. The 1-degree region that was mentioned earlier was chosen arbitrarily, so in the future, we will consider testing out different radii to see if we can find additional associated stars. Lastly, we would want to improve our methods for removing the contaminants in our data, such as the Sagittarius stream and the globular clusters. Thank you.
Thanks.
Time for 1 or 2 questions, audience. I have a question for you guys. So what particular models did you guys use for your isochromatics?
So we took the model off of this website called Parsec. So they use a formula generated from previous research, and we just use that to generate the isochrones for our projects.